All right, Algebra, we're going to go through Unit 7, Lesson 1. So if you want to open up your workbook to page 4, we're going to take a look at this lesson today. You're also going to need your graphing calculator. So grab those things, and here we go. Our learning focus today, taking a look just here, is to find patterns in the equations and graphs of quadratics. Specifically, what happens to the graph of f of x equals x squared when the equation is changed by adding, subtracting, or multiplying by a constant. Okay, that's what we're trying to figure out today. So if we change up this equation, what's going on? Here is our opening problem. Optima Prime is designing a robot quilt for her new grandson. She plans for the robot to have a square face. The amount of fabric that she needs for the face will depend on the area of the face. So Optima decides to model the area of the robot's face mathematically. She knows that the area A of a square with side length x units, which could be inches or centimeters, is modeled by the function a of x is equal to x squared units. All right, we know that, right? So if we have a square and we know the side length is x, that means if it's a square, the side length is also x. So the area would be x times x, or x squared units on the inside, right? We can model area using length and width. Okay, so the first question is, what is the domain of the function a of x in this context? So what sort of x values make sense for this kind of situation, or maybe what kind of x values don't make sense for this situation? Think about that for a second. And I think what we're trying to go at with is like negative numbers wouldn't make sense, right, for the length of a side. So we're going to want to stick to whole numbers. We could technically have 0. That would be kind of silly, right? You wouldn't have anything, but 0 is really the lowest number. You wouldn't have a robot face at all, but that might be the lowest it could be. And then how big could we make it in inches or centimeters? We could really go off into infinity. So in interval notation, we could have 0 to infinity, hard bracket, soft bracket. If we wanted to write it as a inequality, we could do x is greater than or equal to 0. So something like that for the domain. All right, getting us going, getting us thinking. Here we go. Number 2, match each statement about area to the function that models it. Okay, go ahead and take a pause for a second and go ahead and do that matching. And then we'll come back and talk about what goes with what. All right, so when you look at matching these together, did you put the length of each side is increased by 5 units? So we're just increasing the length of the sides, and then that's what we're going to have to square it. So when I think about this one, right, I'm taking this side length and I'm increasing it by 5, which means I'm taking this side and increasing it by 5. So when I find my area, it's going to look an awful lot like number 2 right here. The length of each side is multiplied by 5 units. Okay, so if I think about what that's going to look like for B, I have my length of my side and I'm multiplying it by 5, which means I'm doing the same thing here. So I'm going to multiply the side lengths by 5 and this times 5. When I multiply them together, I have 5x times 5x, or 5x squared, just like that. All right, let's keep going. If we look at the next one, the area of a square is increased by 5. So that we're taking the area, which we already have. So we have area of the square, we're talking about x squared, and we're going to increase that by 5. So that looks an awful lot like 4. All right, and then if we look at the last one, hopefully that goes with number 1. That's the one that we have left. So we are going to see the area of the square is multiplied by 5. So x squared, and then we'll take that whole area, the x squared, which is our area, we're going to multiply it by 5. And that does, in fact, go with number 1. Okay, do those make sense to you? Take another look if you need to. And here we go. Optima started thinking about the graph of y equals x squared in the domain of all real numbers. So rather than limiting it to this specific robot quilt situation, we're talking just in general about this equation over the entire graph. Make a table that contains both positive and negative values of x and graph the function. What features do you notice? All right, we're going to give ourselves a little table going on here. So we've got x, and then this is going to be y. And in this case, y is equal to x squared. So when we're making our table, we just want to keep that in mind. That x squared is going to be worth our y. All right, so let's think of some values. You know, we can kind of go with the classics, -3, -2, -1, 0, 1, 2, and 3. Give ourselves a good range of numbers. And then we're going to think about what each of those numbers would be squared. So -3 squared, 9, -2 squared, -1 squared, 0 squared, 1 squared, 2 squared, 3 squared, right? And we see that beautiful symmetry that we get in our quadratics. We've started to notice that already. And so let's take a look then at what this graph is going to look like. Let's sketch ourselves a set of axes, get ourselves a y-axis, and let's get ourselves an x-axis drawn in there. Okay, so if that's what we got going on, we're going to graph -3, 9. So go ahead and get this graphed on yours. negative 2 comma 4, negative 1, 1, 0, 0, 1, 1. Okay, and so we see that nice parabolic shape. Let's see if I can get a good one. There we go. Ooh, almost. Okay, hopefully yours looks a little bit better than mine, but we get that parabolic shape as we put that together. Okay, what other things can we notice? What features do we notice about this graph? What are some things that we can pay attention to as we see this? Okay, so things you might notice. Hopefully somebody's pointing out that this is the vertex. Okay, that's the lowest point. This is also can be our minimum. This graph has a minimum. That's got a vertex. The graph is curved. It's got a parabolic shape, right? We have a parabola going on here. It is symmetric. We've talked about this before. We can see the symmetry in the table, right, where we have our matching points around our vertex and also across. If I were to cover up half and flip it over this way, right, we could flip right onto each other. That's how we're able to graph relatively quickly. It's kind of bugged me there. Okay. Let's see. Yes, we've got that matching symmetry. We've got our minimum. Yeah, I think you found most of the things. What's the x-intercept? 0, 0. What's the y-intercept? 0, 0. So those are a lot of our key features that we've noticed as we are taking a look at this graph. All right, let's keep going. Optima began wondering about how many changes to the equation of the function, how changes to the equation of the function, like adding 5 or multiplying by 5, will affect our graph. She decides to make predictions about the effects and then check them out, and you are going to do the same. So go ahead and turn the page to the top of page 6. You are going to make your own predictions of how the graph of each of the following equations will be the same or different from the graph of y equals x squared. So pause the video just right now. Go ahead and fill in this table. So this is something you're going to do on your own. There's no right or wrong answers to this. You're just kind of thinking, gosh, what do I think is going to happen to this? How is it going to be similar? How is it going to be different? How is it going to move or change? Or what's the appearance going to look like? Do you think it's still going to be a parabola? Do you think what's going to be different about it? So do some thinking. What's going to be the same? And what do you think is going to be different? Just take a couple minutes. You don't need to make tables or graphs or anything. Just what do you think? So hopefully you've completed this whole table. Again, I'm not going to tell you, but this is where you're kind of getting down your initial ideas. All right, so let's take a look then at number 5. Optima decides to test her ideas using technology. So we're going to be using our technology as well. She thinks that it's always a good idea to start simple. So she's going to start with this equation, y equals x squared plus 5. She's going to graph it along with y equals x squared in the same window. Test it yourself and describe what you find. All right, time to power it up. So get your calculator going on here. And in case you haven't been using your calculator in a while, or if you're using a school calculator, let's reset the mem real quick just so we don't have a whole lot of mess. And just as a reminder of how to do that, we're going to go to second. We're going to go to the plus sign, which is mem. So you should have this menu pop up. We're going to pick 7 reset, all RAM, and number 2 reset. So just to run through that one more time real quick, if you needed it, second, plus sign for memory, 7, 1, 2, enter. All right, so that means everything's going to be nice and cleared out. There shouldn't be anything in your y equals now, no messy graphs or different windows. We should all be really in the standard part. So let's go ahead and put our typical one, the y equals x squared, in our first graphing spot. So we're going to do x. Remember the x is right here next to the alpha key way up here at the top. So x squared, that's our base one that we're going to be using over and over. So let's keep it in this one in the blue. And then we're going to go down to this one and we're going to put in x squared. So x squared plus 5. And so we've got our 2 different equations that we're going to put onto our graph. All right, so once they're both typed in, we're going to go to graph and we're going to watch them graph both and see what we notice. Okay, there's our first one. There's our second one. Okay, so what do we think? What things do we see? What do we think about it? We can even zoom it out just maybe a little bit further if we want to change our window. Keep the x probably the same, but if we wanted to go up a little higher on the y, because it seemed like it was kind of towards the top, like what if I make it 50 in my y max? Let's pop back to the graph and see. So there's that one, and there's that one. Okay, so what observations do we see? What kinds of things do we notice? Okay, yep, it seems to be shifted up, and let's see if we can get this sketched on here as well. So if we've got this going on, here's our graph. Okay, our first one was here, right? 0, 1, 1, 2, 4, right? 3, 4, 3, 9. 7, 8, 9, just like that. We can do this is our basic x squared. Whoops, there we go. Ignore that one. Got that one. And this one. So this is our basic x squared parabola. Okay, we got it kind of long and tall. And so then what is this going to look like? What kind of points do we have? What do we notice about it? It seems to be a little bit higher on our calculator, right? So if we go to our table, we've got some different values, right? Here's the blue one, right? That's our initial. Here's our second one. So let's look at the table and see if we notice anything about that. And how I got there, again, just remember second and then the graph button or table. Okay, so we're looking at the red numbers and how do they compare to the blue numbers? Yeah, they all seem to be 5 bigger. So every single one of these points is exactly 5 higher. So if we go ahead and add this to our graph, this one, instead of being at 0, is at 1, 2, 3, 4, 5. Instead of being at 1, this is at 1, 2, 3, 4, 5, 6. Instead of being at 4, this next one's going to be at 9. Did I graph that one crazy? I think I did, huh? That's where that one should be. I thought that looked a little strange on my parabola, huh? So 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Goodness. All right, you guys got to keep me honest here. Got a hot mess going on here. Okay. So that's not quite the right point, but we get the idea. Okay. So we've got this one then coming in. All this pressure. All right. So we've got this. And so it's just the whole graph just shifted up just a little bitty bit. Hopefully yours looks a little bit better than mine. Okay, so let's write something in there. So we would say that y equals x squared plus 5 is 5 units above y equals x squared. Okay, cool. Let's keep going and see what other changes we can make. All right, number 6, knowing that things make a lot more sense with repetition, with more representations, Optima tries a few more examples like y equals x squared plus 2 and y equals x squared minus 3, looking both at a table and a graph for each. What conclusions could you draw about the effect of adding or subtracting a number to y equals x squared? Carefully record the table and graphs of these equations and explain why your conclusion would be true for any value of k given y equals x squared plus k. Okay, so they're giving us a lot to do. So let's take a look at y equals x squared plus 2 compared to y equals x squared and y equals x squared minus 3 compared to y equals x squared. So for each one, let's go ahead and get our base equation on here. And do the same thing over here. All right, so let's get y equals x squared on there, and I'm going to be careful this time to do a nice accurate job. So 0, 0, 1, 1, 2, 4, 3, 9. That would go just there, right? Negative 1, 1, 2, 4. You're graphing this as well, right? Get your graphs on there. So this is my base parabola. Okay, y equals x squared. And then we'll think about what this one is going to look like in a second as well. And then over here, we've got this one. 4 away, and then 4, 5. Okay, got them on there. Okay, so those are our y equals x squared, right? That's our basic one, just there. So what do we think is going to happen if I have y equals x squared plus 2? What do we think that's going to look like? So let's take a look then at our y equals at our equation. So we're going to change this. Instead of being x squared plus 5, let's look at if it were x squared plus 2. Do you have some thoughts or ideas about what you think might happen to that? And we can pop over to the graph and see. So there's my x squared, and then there's my x squared plus 2. So let's zoom back in a little bit so we can see exactly what's going on a little more carefully. And so we look and see it's exactly 2 above. Is that what you were predicting? Hope so. So if we look at how we are going to graph this, it's going to be exactly 2 above each one of these. And if we look at the table, we're going to see the same thing. So if we go to second table, we can look at what our equations are going to look like. And so we'll copy that down as well so that we have a good example of a table. So we have our x's, right? And we can actually go back just a little bit. So we have in x, we've got negative 2, negative 1, 0, 1, and 2. We'll just do a few. And for our, if we just do x squared, what do we get? And then what do we have if we do x squared plus 2? Okay, well, let's get those filled in. So if we have just x squared, it's going to be 4, 1, 0. My pen's running out. 1, 4. And if we look at what we have over here for this one at -2, we've got 6, 3, 2, 3, and 6. All of these are exactly 2 bigger than the one before it. So let's see if we can finish our graph a little bit. We're going to make each one of these 2 higher than the one before. And so that's going to be my parabola, just like that. Awesome. Okay, let's do the next one and take a look and see. So on this one, we've got x squared minus 3. Thoughts and ideas about what that might look like? I'm sure you're right. I know you guys. I bet you have this exactly figured out. It's going to be 3 lower than everything. So if we look at our graph, 1, 2, 3, right? 1, 2, 3. Everything's going to come down 3 from where it is right now. 1, 2, 3. Nothing else about it is changing. Just everything is shifting down. 1, 2, 3 from each one. So we're going to see our parabola just below the other. Whoops, 1, 2, 3. Yeah, okay. So we've got that one in there. Let's see what that looks like if we put it into our technology here, into our graphing calculator. -3. Make sure you're using the subtraction key in there. All right, let's go to our graph. There's the first one. There's the next one, exactly as we thought. And let's take a look at our table and see if we can fill out a table for this as well. So if we have our x, we have our x squared, and we have our x squared minus 3. So let's do the same set of numbers just to keep it easy for ourselves. We've got 4, 1, 0, 1, 4. And then for our x squared minus 3, let's take a look. We've got 1, we've got -2, -3, -2, and 1. All of these are exactly 3 lower than the one before. So it seems to hold true, right, that when we have an equation like this, so y equals x squared plus k. Let me make sure you can see that. There you go. Okay, y equals x squared plus k. The k value is going to shift the graph. So this shifts the graph of y equals x squared up k units if k is greater than 0, or when k is greater than 0, or down k number of units if k is less than 0. So that's what we've got going on with those. Okay, that's the first piece. All right, let's keep rolling. We got more graphs to do. So turn in the page. We've got a few more explorations to look at. After her amazing success with addition in the last problem, Optima decides to look at what happens with addition and subtraction inside parentheses, or as she says it, adding to the x before it gets squared. Okay, so using your technology, decide the effect of h in these equations. So if we have y equals x plus h inside the parentheses squared, and y equals x minus h, that quantity squared. So if we think back to when we saw this, right, it was in this one, when the length of the side was increased by 5 before we squared it. So that's the kind of thing that we're looking at, is that type of an equation. So we're going to use these 2 equations and see what we notice. So before we do that, of course, we're going to start with our base equation. And so we're going to have our x values, we're going to have our x squared values, and then we're going to have our x minus 2, in this case, that quantity squared values. We're going to set up a table over here the same, x plus 1, that quantity squared, as our columns. And we'll start out kind of the same way, -2, -1, 0, 1, and 2, so that we can have something to compare it to and see what we're noticing about these values. Let's also get our graph going on. Get our y and x axes on there so we can see, and go ahead and get a y equals x squared graphed on there. All right, on each one. So you're doing this as well, just right now. I feel like I'm getting better, right? A little more consistent with every single one of these that I do. Okay, 1 and 1, 1, 2, 3, 4. 1, 2, 3, 4. So this is our base setup for these, and then we'll see what happens when we start to put this into it. Any thoughts, any guesses? Because it looks a little different than what we did over here, right? It's in the parentheses now instead of not being. So let's check it out. Let's go to y equals. We've got our base equation in there, y equals x squared. And then down here, I'm just going to clear this out so I can get it in there just accurate. So parenthesis x minus 2, and then I'm going to square that. So this is my equation that I'm going to be graphing for that part of it. Okay, let's check it out and see what happens on our graph. There's the first one. We're familiar with that. Oh, check that out. It's moved just slightly to the right. How many to the right? If we look at this really carefully, it's slid over 2 to the right-hand side. All right, 1, 2. 1, 2. 1, 2 is actually back on top of that one. 1, 2. 1, 2. All right, we're getting them all graphed in there. Nice, nice. Okay, and so then let's take a look at our table of values. Go to second table and let's check out what we end up with. So at -2, this one is at 16. At -1, it's at 9. At 0, it's at 4. And then it's at 1. And then it's at 0. So we kind of see this like pattern, right, where these numbers don't happen until a little bit later, right? Their matching counterparts are down a little bit, 2 down on the right, a little further, or I should say 2 this way before we get to that same exact number. So if we have, -2, 4, I guess, right, was here, but that doesn't happen till 0 on this one. So we can kind of see that same pattern in this table. So what do you think about this one? Let's think about this another time. Got a theory? All right, I don't want to spoil it for you. Let's go back to our y equals and let's type it in. So instead of being -2, we're going to say +1. Let's go to our graph. Were you right? Yeah, it went left this time. So this one went to the right. And this one ended up going to the left. 1 space, right? Just over 1 spot on every single one of these dots. So go ahead and get those new points sketched in there. Get your new parabola sketched in there. Excellent. And let's go to our table and check out what our numbers are. So at -2, we're at 1. And then here's our 0, 1. And then our 4 and a 9. So we can kind of see that same shifting happening, but it's going the opposite way, right? It happens a little sooner than it would in the regular graph. Okay, so let's see if we can kind of make some synthesis out of that. So generally, what can we say about h? Okay, so let's find a little spot to write this. Maybe we want to do it way up at the top. Would that be okay? Okay, so we've got y equals x minus h, that quantity squared, shifts the graph of y equals x squared to the right. When does it move it to the right? But we have to look at this equation, right? It's minus in the middle. So this one's minus in here. And so the number that I'm looking at is 2. So it goes to the right h units when x is greater than 0, right? Or when h, I should say, h is greater than 0. And left when h is less than 0. It's a little counterintuitive though, right? Because when h is less than 0, it's a minus a negative, and so it ends up looking like a plus. So I think this one's a little bit tricky just because it's a little bit counterintuitive, right? That this is really the same as y equals x minus -1 squared. So my h value here is really a negative number, and that's why it's going to the left, because the basic equation has subtraction in the middle already. So whatever I'm putting here, right, this is just a 2, goes to right. In this case, it would be a -1, so it ends up looking like a plus, and it's going left. Okay, well, Optima agrees. She thinks that this was a little bit tricky and had hoped that multiplication was going to be a little more straightforward. She decides to start simple and multiply by -1. So she begins with y equals -x squared, predict what the effect is on the graph, and then test it. Why does it have this effect? All right, well, let's go ahead and put it in. There isn't any place really for us to write this down, but let's see what we notice. Let's go here. So we've got x squared. We're going to clear this one out. We're going to put in a negative. Make sure you're using the negative sign, not the subtraction. Negative x squared We're going to put it in there. We're going to go to our graph. There's my first one, and there is my second one. Was that what you thought was going to happen? So if we just do a quick sketch just to help us remember, okay, our original parabola is going to go this direction. We'll just make this one a quick one. This is y equals x squared. And then if we draw in what we just saw, we can see our other one. And this is y equals negative x squared. So that negative out in front changes which way it opens. So this is a reflection over the x-axis. And this is what we call when it opens down and it has a maximum, right? This is what we call when it opens up is the words we use, and it has a minimum value just right there. Okay, good to go. We've got just a couple left and then we'll be ready for takeaways. You guys are doing amazing. I know it. All right, over here. Ready? Okay. Optima is encouraged because she was able to figure out the last problem. She decides to end her investigation for the day. We've done a lot of work for sure by determining the effect of a multiplier A in the equation of y equals ax squared. Using both positive and negative numbers, fractions, integers, create at least 2 tables and matching graphs to determine the effect of a multiplier. All righty, well, we're going to use these two if that's all right with you. And we are going to go ahead and get this all set up for ourselves. You know what to do. And we are going to put on our base equation. Oops. I know I can't talk and graph at the same time. All right, so there's my basic y equals x squared equation. And over here as well. 2, 3, 4. Okay, so last chance to see what we think is going to happen with this one. Ooh, that might be my best parabola of the day. Okay, y equals x squared. That's what we've got. And so then we're going to think about our tables, right? So we're going to have x, we're going to have x squared, and in this case, we're going to have negative 4x squared as my columns. So we've got like a double table going on, negative 2, negative 1, 0, 1, and 2. Get our basic ones in here. We'll do over here x squared, and 1/4 x squared. All right, and then let's go ahead and grab our technology and see what happens when we put these in and see what's going on with that. Okay. So keep our basic one basic, and we're going to put in negative 4x squared. All right, take it away, graph. Here's my first one, and then, whoop, yeah, okay, well, it's upside down, right, which we knew was going to happen, but it also seems to be a bit more narrow, doesn't it? It seems that it's gotten a bit skinnier. So let's go back real quick. What if I change it and I don't make it negative just to make it easier for ourselves? Let's delete this off real quick and see what this would look like if it was just 4x squared. It is quite a bit more narrow, isn't it? So let's see what happens with our values when we look at this sort of thing. So I'm going to go back and change it to what we thought it was going to be negative 4x squared. Goodness, all kinds of things going on over here. Okay. And let's go to our table and see what we have for values in here that we can fill in. So, because that may help us get it onto the graph. At negative 2, it looks like it's at negative 16, negative 4, 0, negative 4, negative 16. Oh my goodness, I don't have very much graph space on there. I didn't do a very good job of planning ahead, huh? But I've got this part, right? So it's here. And instead of just being a jump of 1, right? This little distance has always been like over 1, up 1. When I go over 1, now I'm going down 4. 1, 2, 3, 1, 2, 3, 4. So we're going to put it like right there. And over here, the same, right? And so that distance is much more narrow. And then to get to the next one, it's 12 more, right? Before I was just going up by 3, right? 1, 2, 3. I go over 1 and up 3. So over 1, up 1, over 1, up 3, over 1, up 5, right? It's that linear pattern that we saw in the previous unit. But in this one, it was going over 1, up 4, and then over 1, up 12. So the next one down is going to be like way down here. It gets super, super skinny, super, super steep. So we've got this kind of a graph that's going like that. So if we notice, we've got a totally different ratio right between these. We're getting much, much more steep as we're looking at this with our number out in front with that negative 4x. So it's upside down because of the negative, but then this 4 seems to be making it very narrow as we're looking at it compared to this graph, right? Our distances between some of these numbers are getting to be different, right? So instead of being, like I said, 1 and then 3 and then 5, it's going to be 4 and then 12. And then anyone know what the next one's going to be? 20. Yeah, so we have that factor of 4 at play. So what do we think is going to happen over here? Let's bounce over here to y equals. We're going to change this. We're going to put in 1/4. I'm going to do 1 divided by 4 in parentheses, x squared. We're going to throw it on the graph. There's my first one. Whoa, there's my next one, right? So let's look at the table. Way wider. Is that what you were expecting? Let's check it out. So at -2, we're at 1. At -1, we're at 0.25, 0, 0.25, and 1. So we can see we don't have very far to go. So from -2, I'm just only going to go to 1. At -1, I'm at 0.25. I'm here, 0.25. And at 1, and I might need to get another one off of this table. So I'm at -3, I'm at 2.25, like here and like here. So we have this really wide base on this parabola. So how do these numbers compare? Yeah, these are all 1/4 of what x squared is, right? That distance, instead of going over 1 up 1, I'm only going over 1 up 1/4. It's 1/4 of what it was over there. So we see that. Okay, so this seems to make it really wide, really, really wide. Okay, we have, in this case, what they call a vertical stretch. And in this one, they call it a vertical shrink, which is kind of a strange word, but let's write those down as well, just so we have that. So vertical stretch, and this one is a vertical shrink or a compression. Sometimes we hear that word being used for this, and that one actually makes more sense. It's almost like we took this one and squished it, compressed it, right? And then this one we took it and we stretched it. So those are some of the words that we're going to use to describe what you're seeing right there. All right, you guys, we've made it to the takeaways. You're doing amazing. Let's see if we can get this all filled in, and then we'll take a look at the retrieval so you can get started on the homework. Okay, so here are the takeaways. So x squared plus x, what happens? This is a vertical shift, and let's make it really clear. So if k is greater than 0, it's going to go up. If k is less than 0, it's going to go down that number of units. Okay, if it does this, right, this is the regular form of the equation, y equals x minus h, that quantity squared. This is going to be a horizontal shift right h number of units. In this case, we're going to see a horizontal shift left h number of units. So far, so good. Okay, I don't know why the other half of our table is over here, but it is. Let's jump over to the other side. When we have a negative out in front, or any kind of a negative a value just like that, we are going to have a reflection over the x-axis. So reflection over the x-axis. And in this case, we're going to see a couple different things. And so if we have a is greater than 1, right? So we have a big number, 2, 3, 4, 2.5, anything like that. It's going to be a vertical stretch by a factor of a. Okay, that parabola, in this case, a vertical stretch, means that this is going to get narrower. Okay, if a is less than 1, we are going to see a vertical, and let's go ahead and call it a compression because I think that makes more sense. Shrink sometimes, or compression. And then by a factor of gets used so much, they abbreviate it by a factor of, BAFO of a. And in this case, it's going to get wider. Okay, quick recap of some vocab. We know that each of these has a vertex. This is the maximum or minimum point on a parabola. And we've talked about the line of symmetry. That's that vertical line that goes through the vertex that divides the parabola into two congruent parts. Awesome. All right, y'all. You're going to have a chance to practice a lot of those things in the set. I think you're going to get a chance to kind of look at those and see what we think is happening. You're going to have to do some analysis, right? So if I give you the table, can you see maybe what's happening between some of these? And so how do we write that equation? So make sure you come back to your notes as you're working on the set to try to figure out how this might be changed. So let's take a look at the retrieval and take a look at what we've got going on here. So draw a line of symmetry for the graph, state whether the graph has a maximum or a minimum, and provide the coordinates. All right, easy enough. So line of symmetry is going to be the part that divides it. So that's going to be just right here. So in this case, our line of symmetry, our axis of symmetry, okay, our AOS is going to be x equals 4, right? It's a vertical line through there. Does it have a maximum or a minimum? Well, in this case, it's got a minimum point. And the minimum point is just located at the vertex. Technically, the minimum is the y value of the vertex, but the whole point here is going to be 4, 0. So the minimum value is 0, but it has a minimum point. Okay, the coordinates for that point. All right, take a look at this one. We've got a axis of symmetry going just right here. Okay, we can draw it right in there. Our axis of symmetry is going to be at x equals, if this is 0, 1, 2, 3, -3. Okay, in this case, we have a maximum, and it's located at -3. 1, 2, 3, 4, 5. I think I did that right. Double check me there. All right, and then let's take a look at the last couple of questions on the retrieval. So graph the linear equations and explain your strategy. All right, number 3 is a throwback form, right? This is in our point slope form that we've talked about, or in our sequences form. Okay, we know that this right here is my slope, or my common difference. And we know that these two things go together to make a coordinate point. But just like in what we saw in the lesson, this is in the opposite, right? It's x minus this value, point slope form. So if in this case, we're going to have y is equal to m times x minus x1 plus y1 is what we end up with. And so you can see it's subtraction in that equation. So this, we need to make sure we think about that as -3. Okay, as we're looking at that. So here's what we know. If we have a graph, let's go like here maybe, huh? Okay, we can graph the point -3, 7. We know that's one of the points that is on this graph. So I'm going to graph -3, 7. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. That's going to go there. And then it has a slope of -4. So slope of -4 over 1. So we're going to go down 4. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. And so that's going to be the graph of my line using that point slope form that we did before, right? So x1, y1 is a point that's on that graph. This one is in standard form. Good. And so we can find the two intercepts pretty easily using that cover-up method, right? If x is equal to 0, can we find y? And if y is equal to 0, can we find x? So if x is 0, -4 times what is 24? -6. And if y is 0, 3 times what is 24? We've got 8. So you're going to pop it on the graph. Like this. Hopefully I did enough. We'll find out. 1, 2, 3, 4, 5, 6. Ooh, I can't count. 1, 2, 3, 4, 6, 7, 8. Okay, so that's my 8, 0. And then I've got 0, -6. 6, just right there. We can graph our two intercepts. Boom, boom, done. Okay, so you've got homework to do. Okay, ready, set, and go. Do your very best. Go back and look at your notes, right? This part should be pretty easy, finding those vertexes, the set. Really look at how are these changing or what's happening with this. Maybe put it on a graph, see what you notice. They give you some places to do some of those things. So really put your best effort into it. And then for these, you can graph those lines. I think that's not going to be a problem for you. Okay,